Hello everyone and welcome to lesson 4.1. So today we are starting chapter 4. I know it's kind of weird to start a chapter in a subplan, but we are just going to work with it. We're just going to go with it. In chapter 4, we're starting to talk about integration. Think of integration as the second big topic in calculus. So if we simplify calculus, it's basically learning about differentiation and integration. And if you think back to those two problems at the very beginning of the course, one was trying to figure out, okay, what is the slope of a tangent line? That's what we did with differentiation, finding derivatives. And the second problem was, how do you find area under a curve? That's what we're going to be solving in this section with integration. So section 4.1, we're going to be talking about antiderivatives and indefinite integration. We need to start with indefinite integration. Think of it as kind of the simpler version. And then eventually in a couple days, we're going to talk about definite integration. This term right here, that's a pretty important one, antiderivatives. Think of this as, okay, you know how to find a derivative. Finding the antiderivative is basically that process, but in reverse. When we talk about anti-differentiation and integration, those are interchangeable. Okay, so for this section, you are allowed to think of anti-differentiation, as about equal to integration. We will talk how, maybe there are some slight nuances, but it's the same process. Overall, it is the same process. So anti-differentiation, the process of finding your antiderivative, we're going to use interchangeably with integration. Okay, so these are some of our objectives. We're going to write the general solution of a differential equation and use indefinite integration for antiderivatives. If you do not know what some of those words mean right now, that is okay. We are going to define a lot of these together. And then we're going to be using basic integration rules to find antiderivatives. So by the end of this lesson for 4.1, you will have access to all these basic integration rules. A lot of them you already kind of know, but you know them in reverse. So even homework 4.1, you're already going to be doing a whole bunch of different types of problems, which is really cool. We are not going to do this objective today, but that's something, finding the particular solution. We're going to do that not exactly tomorrow either. We're going to end up doing that early next week. So that's what you can look forward to when we're all back together next week. Okay, so let's get into this a little bit. What do I actually mean by an antiderivative? Your textbook definition is down here. Up top, we're going to explain that a little bit. So to find function capital F, anytime you see an uppercase letter, we're going to link that with it being an antiderivative, whose derivative is 3x squared. You might use your knowledge of derivatives to conclude that capital F of x is, so if I know that my derivative is 3x squared, what would my original function have to be? Hopefully you're thinking x cubed, because you might be like, Ms. Cron, why are you going back and forth so many times? That's okay. I want to make sure that this is super clear, because if I take the derivative with respect to x of x cubed, I end up getting 3x squared. So you see how this is kind of this process in reverse? They're giving you your derivative and they're asking you, what was that original function? What is your antiderivative? Okay, so capital F is an antiderivative of a function when the derivative of that function equals f of x. Okay, so that's what we mean by antiderivatives. F of x was called an antiderivative because there could be others. So something that's a little bit weird with antiderivatives is that I could have multiple functions that have the same derivative, right? So for example, I could say, hey, I have this function f of x equals 2x squared plus 3. And I have this other function, g of x, which equals 2x squared minus 4. What would the derivative of each one of those be? Well, your derivative of f of x would just be 4x, but your derivative of g of x would also just be 4x, okay? So you have this piece over here that could change. I could have one antiderivative that actually has many different functions, okay? So generally we use this form, g of x equals f of x plus c. All right, so you're finding your antiderivative, that original function. This c represents some kind of constant. I could have any constant. I don't know if there's a constant or what that constant is, because again, over here, that's what we were kind of talking about over here. I could have multiple functions that actually have the same derivative. So we have to kind of tack on that c, that constant. And then again, just remember uppercase means we're talking about derivatives. So uppercase represents antiderivative. All right, so that's exactly what this theorem down here is saying. This is the same thing we wrote up there. That's what you're going to find exactly in your textbook. I do want you to read through this textbook section, so that's something that I'm assigning for this too. Because I'm not there, I want you to use your resources, and I really want you to dig into this first chapter, okay? If you do that, you will be set up really, really well for the rest of this chapter. So please make sure you do that. Some of these things will look very, very extraordinarily familiar when you're skimming through that textbook section, but do it, okay? All right, let's keep going with this. We have a couple terms. Yes, there are a bunch of notes when we're starting this section off. That's okay. Something that you might see or something that I might say is family of antiderivatives. That's basically that concept where, I could have multiple functions that would have the same kind of antiderivative, something like that. Okay, so your example of this would be I could have g of x equals x squared plus c, right? I could have that c be anything. It could be positive, it could be negative, it could be big, it could be small. But this is kind of like a general family of antiderivatives. Okay, it's that function, that antiderivative x squared, but then plus some kind of constant. Your constant of integration. So that's kind of the fancy name for it. That just is that c value. Okay, so again, positive, negative, big, small, could be anything. And integration is the same process as anti-differentiation. Okay, so link those ones right now. They're just different words that are explaining the same thing. General antiderivative. That would just be like g, capital G. That is some kind of function. And then today we're really going to stick with general things. We will talk about particular equations and solutions in a little bit. I'm so sorry if you can hear that helicopter in the background. Just ignore it. Okay, so I could have a general antiderivative like capital G. And then differential equation. This was something that popped up as one of the terms in our objectives for today. It is an equation with x, y, and or derivatives of y. So for example, I could have y prime equals 3x, or I could have y prime equals x squared plus 1. Those are just some examples, right? So you have a derivative in there, you have an x term, you could have also another y term in there. Think back to implicit differentiation, where we had problems that had both x's and y's kind of scattered throughout. So a differential equation is just any equation that has those things in it, okay? You have already used a lot of differential equations. Now we're just giving them a specific name. Okay, and then the last term here would be general solution. So, for example, if you have a general antiderivative, your general solution could be 2x. Okay, so we would say you have a general solution of a differential equation that would maybe look something like this. Okay. So lots of functions, lots of terms. Best way for us to really understand this is just to get into some problems. I'm going to split this video up into 2 parts. So we're going to do one example, and then at some point I'm going to split it up so you don't have to watch 40 minutes all in a row. So let's start with this one. Find the general solution of the differential equation y prime equals 2. And I'm pretty sure I meant to not show you this picture, but you get to see the picture from the get-go. So what we want to think of here, if they're saying y prime is 2, what functions have a derivative of 2? Think this through. Hopefully you're thinking of something. What function has just a derivative of 2? Maybe you said y equals 2x. Awesome. This just represents an antiderivative. It's not the antiderivative. Because, as you can see in this picture over here, well, when c equals 0, then I just get y equals 2x, that line right there. But what if I had 2x plus 2? What if that was actually our equation? Well, then your line would look like that. You still have the same slope, though, right? You still have the same derivative. What if c was -1? Well, then your line would look like this one over here. Same slope, but different antiderivative, okay? So for this one, your general solution then would be y equals 2x plus c plus that graphical, that constant over there, okay? And again, I like this graphical view for us. It just helps us to kind of visualize what's going on here, right? I have a bunch of functions that have the same slope, but they're different, right? Those are all 3 different functions, and that c could be anything, okay? So that is example 1. We do have a little bit more notation, so we're going to chat through the notation, and then we will pause this video. So here they're going to chat more about differential equations. These would be in the form dy dx. We're going to say that is equal to f of x. Okay, so stick with me here. F of x represents a function. Now that we're talking about integration, some of our functions will be derivatives of things, okay? So sometimes our starting place will be a function, but maybe that is a derivative, and then they're asking you to find your antiderivative, okay? Sometimes we will need to rewrite some things. So if you think about this as, the derivative of y with respect to x is some function over here, we might rewrite it like this. dy equals f of x dx. You might be saying, why am I doing that? Excellent question. Okay, we're going to rewrite it, and we are eventually going to put it in an integration form, into an antiderivative form, okay? I am allowed to break up this dy dx. Again, all that means is derivative of y with respect to x. So on this side, then, I just have a derivative of y. Over here, then, I have f of x, derivative of x, okay? So the operation of finding all solutions of this equation is called integration. I switched them up. Don't write that. It's called antidifferentiation or differentiation or indefinite integration. Those mean the same thing. They're going to be denoted by an integral sign that looks like that, okay? Think of it as an elongated S. Eventually, when we get more into integration, we're going to think about this concept of like summation. So think about this as an elongated S for sum or sigma or summation. Right now, I don't need you to think too much into that, but basically just think, okay, my integral sign is just this big long S, okay? We are going to stop part A of this lesson, continue on to part B for a couple more notation pieces, and then we will get into the rest of our examples. See you there.